Hello everyone, I am Li Qina from the Electronics and Information Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. Today we'll cover section 6.2, the properties of a Laplace transform for continuous time signals. The Laplace transform establishes a relationship between a signal's time domain and the complex frequency domain. Any change in the time domain signal will inevitably be reflected in the complex frequency domain. The properties of the Laplace transform faithfully capture these relationships. Next, we will study, one by one, the 10 properties of a one-sided Laplace transform for continuous time signals. Property 1, linearity. Suppose we have two signals, f1t and f2t, with Laplace transforms f1s and f2s, and regions of convergence sigma greater than sigma 1 and sigma greater than sigma 2 respectively. If we scale f1t by a1, f2t by a2, and then add them together before taking the Laplace transform, we find that the result is a1 times f1s plus a2 times f2s. This means that linear operations in the time domain correspond to linear operations in the complex frequency domain. Property 2, scaling. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we scale the signal by a factor a, forming fat, then its Laplace transform becomes 1 over a times fs over a. Here, a greater than 0 ensures that fat remains causal. The corresponding ROC is sigma greater than a sigma 0. Property 3, time shifting. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we delay the signal by t0 units, forming f t minus t0 times u t minus t0, its Laplace transform becomes e to the st0 times fs. For the one-sided Laplace transform, it is necessary that t0 is greater than or equal to 0. If t0 is less than 0, the signal may shift to the left of the origin, causing the portion of a signal before t equals 0 to fall outside the integration interval 0 infinity. Property 4, convolution. Suppose we have two signals, f1t and f2t, with Laplace transforms f1s and f2s, and regions of convergence sigma greater than sigma 1 and sigma greater than sigma 2 respectively. If we perform the convolution of f1t and f2t, and then take the Laplace transform, the result is f1t times f2t. In short, convolution in the time domain corresponds to multiplication in the complex frequency domain. Property 5, multiplication. Suppose we have two signals, f1t and f2t, with Laplace transforms f1s and f2s, and regions of convergence sigma greater than sigma 1 and sigma greater than sigma 2 respectively. If we multiply f1t and f2t, and then take the Laplace transform, the result is 1 over 2 pi j f1s times f2s, with ROC sigma greater than sigma 1 plus sigma 2. In short, multiplication in the time domain corresponds to convolution, scaled by 1 over 2 pi j in the complex frequency domain. Property 6, exponential weighting. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we multiply ft by an exponential factor e to the minus lambda t, the Laplace transform becomes f s plus lambda, with ROC sigma greater than sigma 0 minus lambda. This means that multiplying a time domain function by e to the minus lambda t corresponds to a shift in the complex frequency domain. Hence it is also called the S-domain shifting property. Property 7, linear weighting. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we multiply ft by minus t, the Laplace transform becomes the derivative of the original transform. This shows that linear weighting in the time domain corresponds to differentiation in the complex frequency domain, also called the differentiation property in the S-domain. Property 8. Differentiation in the time domain. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we take the derivative of ft and then compute its Laplace transform, the result is s times fs minus f0 minus. The proof of this property uses integration by parts from advanced calculus as follows. By repeatedly applying this differentiation property, we can derive the Laplace transform of the second derivative of ft as follows. Similarly, the Laplace transform of the nth derivative of ft is as follows. If the signal ft equals 0, for t less than 0, f to the r of 0 minus equals 0, and the Laplace transform of the nth derivative simplifies to s to the n times fs. This property is essential to master, as it will be used extensively when solving differential equations of LTI systems in the complex frequency domain. Property 9. Integration in the time domain. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If we take the integral of ft and then compute its Laplace transform, the result is as follows. If ft is a causal signal, the Laplace transform of its integral simplifies to fs over s. The proof of the integration property for the one-sided Laplace transform is as follows. You are encouraged to carefully study the proof after class. Property 10. Initial and final value theorems. Suppose a signal ft has the Laplace transform fs with ROC sigma greater than sigma 0. If ft does not contain an impulse or its derivatives at t equals 0, then the initial value f at 0 plus equals the limit as s approaches infinity of s times fs. If the ROC of s times fs includes the j omega axis, then the final value f infinity equals the limit as s approaches 0 of s times fs. Thus, the initial and final values of a time domain signal can be obtained by taking appropriate limits of s times fs in the complex frequency domain. Let's look at an example. Given the Laplace transform fs of a signal ft, find the initial and final values of the signal ft. Using the initial and final value theorems for the one-sided Laplace transform, since fs is a proper rational function, ft contains no impulse or derivatives at t equals 0, the initial value theorem gives an initial value of 0. Because the ROC of s times fs extends beyond sigma equals minus 2, and thus includes the j omega axis, the final value theorem yields a steady-state value of 1/2. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.